Hello everyone. Today I am here to do calculation for the gravitational force. From the above question, we are given height of the astronaut to be 1.7 meters, mass of the earth, distance from the earth, and in the picture it looks like the earth is pulling the satellite as well as the astronaut. The astronaut is standing straight, and what we want to find is the difference in acceleration due to gravitation at his feet and at his head. So let us assume m to be the mass of the astronaut. From Newton's law of gravitation, we can write F to be g, a mass of the earth times mass of the astronaut divided by r square dot r cap. Let's assume this to be equation 1. And we also know that F is equals to ma. Let's assume this to be equation 2. Comparing 1 and 2, we get ma to be g mm over r square dot r cap, and small m gets cancelled, and we get acceleration to be g times mass of the earth divided by r square dot r cap. So now what we want to find is the acceleration derivative of the acceleration a, and what this gives is the difference in acceleration due to gravitational force over a short distance, and that is what we want to find. We want to find the difference in acceleration due to gravitational force in the astronaut at his feet and at his head. So after getting the derivative of a in terms of r, we get this to be dA is equals to minus 2 g mass of the earth times divided by r cube dot dr, and this dr is the small change in distance, which is the height of the astronaut. So now the difference between the acceleration at her feet and at her head is just plugging in the value of g, me, r, and dr. We get the value minus 4.37 into 10 to the power of 6 meter per second, which is very less. That's why we don't feel much of pressure, because the acceleration is less. The difference of acceleration at our feet and at our head is less, so that's why we don't feel much of force over here. Now let's look at the other question. So the other question says that if now the astronaut is feet down at some orbital at the same orbital radius of 6.77 into 10 to the power 6 about a black hole, and the mass of black hole is given to be 1.99 into 10 to the power 31 kilograms, and all conditions are same. Now here we want to find the difference in the acceleration due to gravitation at feet and at the head of the astronaut. So since all other conditions are same except the given mass of the black hole, we can use equation 3, which is dA equals to minus 2g mm dr by r cube. So after plugging in the respective value and dr to be height of the astronaut, we get the value to be minus 14.5 meter per second square, which is much significant than what we calculated earlier. Since the mass of black hole is like 10 times more than our sun's mass, it pulls very strongly compared to the earth, since the mass is very big. And since we experience a lot of difference at the acceleration at the feet and at the head, it's minus 14.5. Just the difference of acceleration at feet compared to the head of the astronaut is minus 14.5 meter per second square, means it's pulling itself with tremendous force, since F is equals to ma. If acceleration is this and mass is to be some value, then then the value is much more significant compared to question number 1. So that's why more people can't survive in the black hole. So thank you, that's it for today.